You are not very bright.
Look who's talking.
Welcome back to Make Stuff for Fun. As always, I'm Brian. You can find LEDs everywhere nowadays. They're used as indicators, lights, or even combined into huge video displays. In fact, it's hard to envision an electronic product today that doesn't use at least one LED. Today I want to give you a quick how and why about LEDs and get you using LEDs in your projects right now. Let's head over to the whiteboard and see how LEDs work and how they're different from traditional incandescent light. Let's take a look at an incandescent light. All right, so we've got an incandescent light bulb. Now how do we use an incandescent light bulb? Well, we connect it to some voltage source. Now that can be either AC or DC, but essentially we just connect some power up to a light bulb and it works. Now light bulbs come in certain voltage ranges. So if you buy a 12 volt light bulb, connected to 12 volts, 110 volt light bulb, same thing, 220, same thing. Match up the voltage, light bulb lights up, that's it, nothing special. Now if we want to model the light bulb is an electrical circuit. Let's do a DC light bulb. Got a resistor. And that's it, just a resistor. That's the beauty of incandescent lights. They don't require any control circuitry. They regulate. Why do they self-regulate? Well, metal has a property that it increases resistance as it increases with temperature. Might not be quite linear, but this is the basic shape of all metals, the resistance to temperature for all metals. This slope might be slightly different, but the point is that resistance increases with temperature, and this has a self-regulating effect on the light bulb. So if we want to look at temperature per time, the temperature is going to start pretty low at room temperature. It's going to get to some temperature and drop, and then it's going to oscillate a little bit, but it's very, very quickly going to reach some kind of steady state. As it goes a little high, the resistance goes up, which drops the current, which makes the temperature go down, and then it goes back up, it oscillates, and it very quickly finds a happy, steady state. It's never going to be in a runaway condition. And that is the beauty of an incandescent light, is that they're self-regulating. And we can call that a voltage-controlled device, because all we have to do is give it the appropriate voltage, and it works. But we don't really want to play with light bulbs. We want to play with LEDs. So how do LEDs work? LED stands for light emitting diode. And the electrical symbol for a diode is a triangle with a line in front of it. Now, a diode is a semiconductor device. So a conductor lets all the electricity, the current flow through it. And an insulator lets none of the current flow through it. Let's say a metal is a good conductor and glass is a good insulator. Well, a semiconductor is somewhere in the middle. And semiconductors, if you put two kinds of semiconductors together, and in this case it would be a P and an N junction, and you apply a high enough voltage across this junction, it starts to allow current to flow. But one of the interesting things is, as the charges flow across this junction, the electrons go from a high energy state to a lower energy state, and this excess energy is given off as a photon. And a photon is just a quantum of electromagnetic energy, and visible electromagnetic energy is we perceive as visible light. So as the electrons go from a higher energy state to a lower energy state, they give off visible light. And this, the color of visible light is determined by the material, the semiconductors the LEDs are made of, but all LEDs essentially work the same. We apply a forward voltage across the LED and we get light out. Now, one thing about diodes is that they have a polarity. We have the anode on this side where we must connect the positive, and we have the cathode where we connect the negative. One property of semiconductors that differs from metals is that the resistance of a semiconductor goes down with increasing temperature. So if you remember, with the metals, we have an increase in resistance with the increase in temperature. But here, with semiconductors, the resistance goes down with temperature. Now that means that the more power it uses, the hotter it gets, and the more power it uses, which is really bad. So let's, we can see that by looking at Ohm's law, V equals IR. So if our voltage, if we try and run it as constant voltage as we did before for the light, the voltage is constant, and well, we start off and the temperature starts going up, so we've got our time versus temperature graph here, and our temperature starts going up, which means our resistance goes down. Well, if resistance goes down and voltage is constant, that means the current's going up. Well, then as the current goes up further, more power is used, things get hotter, and very soon our LED blows up. So we have to control our LED in some way. Now let's look at some of the properties an LED has. Now I said we have to apply a certain voltage across the LED to start it conducting current. Now that's called the forward voltage. Now every LED in the data we look up in the data sheet what it's going to have for its forward voltage, and for many LEDs it's around 3 volts. For many white LEDs, for red LEDs it's closer to 2 volts. And that's where they start conducting. As the voltage goes up, they conduct more and more current. Now, if we look at our forward voltage versus current, they start conducting and then they very quickly go up. So this would be our initial VF, but the point at which the current is super high is not very far away at all. And that means if it's very hard to control an LED by varying the voltage. First of all, usually we're using we might want to use a constant voltage source, at which point we can't vary the voltage. And secondly, a small change in voltage can have a very large change in current. So instead, we try and control the current of an LED. And we call it a current-controlled device. So how do we control the current in an LED? Well, the easiest way is to add a current-limiting resistor. So I'm going to draw a simple circuit here. There's our battery. Got a resistor, and then we've got our LED. All right, So by putting a resistor in series with the diode, we will limit the current. Now, how does that work? All right, so need a little more space on the board. So if you remember, the current through a wire is consistent. Now we know that there's a voltage drop across the diode, a set voltage drop, and we're going to use a constant voltage source. So typically a constant voltage source would be something like 5 volts, maybe 12 volts, could be 3.3, could be 24. Well, for this case, we're going to use a 5 volt source. Now our drop across our resistor is 2 volts. So if you remember, we have one voltage drop across the resistor and another voltage drop across the diode or second device. In our previous example, it was 2 resistors, but it's the same principle. There's a voltage drop across every device. And we know that the total voltage is 5. So the voltage drop across the resistor, okay, we'll call that, let's see, the total voltage is equal to the voltage drop across the resistor plus the voltage drop across the diode or LED. Now we know that the voltage drop across the LED is approximately 2 volts. So our voltage drop across the resistor is going to be 5 minus 2, which is equal to 3. Okay, well now we know that the voltage drop we want across the resistor is 3 volts. How do we decide what resistor to use? Well, we've got to choose what current we want. And this goes back to the data sheet. Where we found our forward voltage for our LED, we're also going to look up the current. And the maximum current is given in the data sheet. And for a small red LED, it'll be something like 20 milliamps. Now, there's no need to run it at maximum brightness most of the time. It can shorten the LED life, but also this is an approximate calculation, and it's not necessarily going to give us exactly 20 milliamps. It might give us 21. So let's err on the side of the caution, and let's use I is equal to 10 milliamps. So the equation we need to use is Ohm's law, V equals IR, and we know that our voltage, first of all, let's rearrange. What we're looking for is R. So R is equal to V over I. We know that the voltage drop is 3 volts, and our current is 10 milliamps. But when we use this equation, we have to use amps for our units. So 10 milliamps is 0.01 amp, and that's going to give us an R of 300 ohms. All right, let's go to the lab and check out what happens when we run a small red LED with a 300 ohm resistor. All right, we've got 10 milliamps and we've got approximately 2 volts. Now let's see if this is what happens when we heat it up a bit. I've just got a regular hair dryer. Turn that on. Okay, so we've just, our current increased by 15% just by heating it up a little bit with a hair dryer. So let's let the current drop back down to 10. Okay, that's probably cool enough. So I've got a 300 ohm resistor here. And I'm going to attach that to our LED. Just like that. Okay, set our voltage to 5 volts. All right, and we're at 10 milliamps. So our calculation was pretty darn close. 10.3, that's a good approximation. Now, let's try the same experiment with the hairdryer. Let it heat up. Okay, Well, as you can see, the resistor stabilized the current of our LED. Instead of going up 5 milliamps, going up 50%, it went up just 0.2 milliamps. So that's excellent. So that shows how a resistor stabilizes an LED. Well, thanks so much for watching. Next time, we're going to take a look at some LED packages, bonding wires, the inside of LEDs under a microscope. It should be pretty cool. So thanks for watching. If you haven't already, please subscribe, hit that bell, and I'll see you next time.